With the package.
Wow!
Wow. Okay. Plastic. More plastic.
What?
Letter. That's it. And
That's it?
And large box.
Crazy people.
There you go. Okay, so I ordered 100 of these. So they've sent me 2 plus plus 22, that's 24, plus 76, that's 100. Yeah, so of connectors, and I really like this. They are better than the ones on eBay. So solder blade, and this time I got the yellow one because... Hi folks, it's been a while since I made a video, so I was thinking making a video of me putting that C64Saver Test JIG board over on a breadboard. And also, yeah, I was thinking of using that chip there for another project. That's a PIC, let's see, PIC 16F690. So yeah, it's got several modules in it, and it has 20 pins. That's 18 IOs. So I bought from a company called Taida over at eBay. Yeah, 683 12F series. So the reason for selecting that one was because they are quite similar in functionality. Yeah, so the principle here is that the microcontroller sets a voltage for the LM317, which again puts the voltage on its output. And the way it works is that the output is always 1.25 volts, or the voltage reference, higher than the adjust pin. So therefore we can control the voltage going into the C64Saver. So by pressing this button here, I can tell the microcontroller to start ramping up the voltage. So let's say the voltage is here, then it starts to step. And it will continue to step until the output voltage, which is here, drops. Then this output voltage here, which is connected here on the output of the C64Saver, is fed in again to the microcontroller. And this is used to change the state of the program, because it's basically a state machine, I think that's what I programmed. So when the output changes, then the state of the program changes, such that if you press the button once again, it will start to, so let's say you press again now, it will start to ramp down like this in incremental steps. And then if the output changes again, it will stop. And also I think I have made it such that I must click twice to do this. But if I click it once, it will only step once. So I can sort of single step it. I thought that maybe it was useful, I don't know. And also there's a light emitting diode here. So that one is blinking when it's stepping up here, and it's continuous when it's continuous voltage. So yeah, it's very easy circuit. So the challenge here was to sort of pick the other. Well, I could use the same one, but I wanted a smaller. It's over here. So yeah. So I will program that, and I'll figure out in the datasheet that PWM must go to pin 5 and such. So I don't know if I want to bother you with that. If you want to know how to, let me know, so in the comment field. Alright, so basically you can see these two LM317s, and then there's a 5-volt regulator. So on the input we have 12 volt, so I take that from the power supply. Bench power supply. So the first thing I do, because I had some accidents here in the beginning, so I made a 1.25 amp limiter. So this is a bit embarrassing maybe, because I don't have a power supply unit. I do have some money for it now, so maybe I will buy one. I mean a lab power supply that we can limit the current. So when the voltage comes in, it's about 12 volt, and it will drop 2 or 3 volt to like 10 and a half or thereabouts, because there's always some drop over the regulators. So yeah. And then there's another LM317, and that one is providing the output voltage. So this is supposed to simulate the power supply. So, and you can see the adjust input here on the LM317. It's connected to a network here up on the microcontroller. So the microcontroller can set the output voltage, because the way this works, the LM317, is that it tries to keep the output always 1.25 volts above the adjust pin. So we can manipulate that. So you may ask, well, how precise is this? But it doesn't matter, because the only thing we want to do is to make small increments until the output switches off, and then we stop. And then we take our precise meter, high precision meter, and then measure the voltage. And then when we click the button again and the voltage starts to go down again, then the output will come on again and the microcontroller stops, and then we will take another reading. So that's the idea here. So we don't need any precise components here really. And this is a, if I remember correctly, I used a 10-bit PWM. So you have like a PWM where the duty cycle, this is the duty cycle here, is controlled. And the frequency here, it's constant. So you only adjust the, you can call it the payload. The thing I'm trying to do here, which is something I should have said in the beginning, is that I'm trying to transform this waveform here into a fixed voltage. So and in reality it's actually going a little bit up and down, but if we filtering it high enough, we will get rid of that high frequency noise. So actually this is a little bit how, if you know delta sigma encoders. I don't remember which of them does what, but if you look at the frequency, if you have frequency here and you have amplitude here, if you want to sample some signal which is in this band down here, down to DC, or let's say 20 Hertz to 20 kilohertz, what you do is that you put a sampling frequency up high up in here, so you get that digitizing noise, if you can call it that, up here. Anyway, that one will be filtered out very effectively. So it's the same principle here. You have a very high frequency, a very short period gives a high frequency. 1 over period equals frequency. So it's about, yeah, what is it? I think it's 19 kilohertz for this project. And the frequency here is like, it's well below 1 hertz, so it's very easy to filter that out. So the thing is here, I get a stable voltage after the filter, low pass filter, and then this low pass filter can set this LO3 setting. That was unexpected, but no worries, it's in there. And we selected dip 8, and you have another dip 8 here, but it says 10F, and this is 12F. And I also checked that it supports that chip. Yeah, and then on the back it says something about socket selection. So if you use dip 8, you must have this configuration. So you can see that I have already done that. Now, if you get to the GPIO port, I think they say pretty early what you have to do, but well, maybe you don't read this data sheet so very closely. So you have Ansel, CMCON 0 register must be initialized, configure an analog channel as digital input. So let me tell you a story about a PIC microcontroller programmer. So nothing is working, so what do you do then? Well, then you set all outputs to all IOs to outputs, and then you make a while loop and you flip the bits every half second. You see blinking. Okay, so it's alive, but so only one of them is blinking. Now from memory I know that that one of them are only inputs, so you can, one of these inputs here is reset input. Even if you're not using it as a reset, it's still an input, so you can't use it as output. What about these 5 left here? Or 4 other ones? Well, now we are getting back to the big Clive thing, what he said. That these modules, they by default, this comparator module is on, so you have to disable that. So let's see what happens. Nothing much yet. Add this analog input selection. So you disable all analog inputs. And what happens then? Now at least we have 4 blinking. So what about that one? I don't know what's going on there. So, but if I had read the manual from the beginning, it said something about. Let me. Okay, maybe I should have looked at page 4 to begin with instead of searching through a whole document. We saw that this first one was on all the time. Well, what's on this? Well, these are the pin summary or the pin outs. So you see these 3 first one. There's analog stuff like this is for sampling, and this is for comparing. Remember that we had to turn off that comparator. Well, if you look at GP2, that's the pin for GP2, you can see there if comparator is enabled, and for some reason it's enabled by default. And analog input mode is also on, I think, or off, I think. Then the output driver will then use Cout as input. So therefore we can't control our CPUs, because a CPU can only do this data bus, and then it will do a write here. So it will take the data, and then on the right pin there it will clock it in. And also I have been talking about the 3-state register, right? That's a 3-state means that the output can be either on or pull it high or low, or don't pull at all. That means that this pin is detached, and to do that the buffer has to be shut down. So when it's on, the drive is on, then it takes data from this flip-flop here, which then you can use the CPU to put data on the databus and then write it into that flip-flop. Actually, don't do that so literally though, but anyway, if you want the output to be Z, that means high impedance, that means that this driver is off, then you must have the output of this flip-flop to be, the inverted output has to be 0. That means you must write a 1 in here, and also you can see that it's the 3-state I/O write. It's like there's missing, something's missing there, isn't it? So let's check ground and 0. No problem. GP1, no problem. GP2, no problem. So GP3, that's an input. GP4, you can see there's no problem. So why is there no LED here? So the question is, do we have GP4 on the output port? Yep. No problems there. So definitely something wrong with this board. I have to figure out what's going on here. So also you have this, it's a row of resistors. It's a resistor pack. Yeah, resistor pack. So they are impeding the current through the light emitting diode. And you can see if I have the meter on this one and the below, you can see it's 1K. And you get 1K on all of them. And the reason for that is that you want 1K through the such that the diode sees 1K. Right. And I've checked RA4, there's no problem there. So that's something. Let's try another diode. Now if we measure the diodes over here, you can see that RA0 is its GPIO 0, goes up to 5 volts, and then on this side goes to 2.5. That's because there's a light diode there, so it's a diode drop over that. Now if you look at this one, RA1, it's the same behavior, same with RA2. RA3 is an input, so nothing there, but RA4, you can see that the signal comes in here, no problems. And you can also see that there's a diode drop here, so why isn't it lighting up? So there must be something wrong with the diode, I think. So 1.6. Yeah, it's not going all the way up to 2 volts. Need about 2 volts, 1.9 volt to turn on a red LED, so yep. What do you know? I think I will use a green one. Why not? Oh, yeah. It looks kind of funky. Yeah. Maybe it's just me, but I'm not looking at this red LED for so long. Yeah. Okay, now it's working again. So, click twice, it starts. And then when the output comes on, it stops. So this signifies the output. And then click twice again, and the output goes off and it stops. Double click. So you can see how this works. So now it's working. And this PWM, I can measure it here, so momentum, there you can see. So changes are so small, it's so difficult to see them. So it's coming along, taking some components here and setting them here. So about this fritzing, you remember last time I used fritzing to plant, but you can see that these components, they overlay each other, so it doesn't look very good. So it's so difficult to plan using this. So I'm using the PCB instead. I had breadboard here, so I'm using PCB. You can see, even though it's not the same thing, yes, you can see that many places I'm lifting pads. So it's because these holes are just drilled and there's no true hole. So what you're soldering to is just a pad. So in contrast to this board, you can sort of see that is plated through hole plated. So I'm soldering this up, and yeah, had many problems with pads breaking by just moving these, so definitely not a good board to use for solder big components that you can bend. Anyway, I have solder that hold everything together. The board is just a board to keep the components on right now. So, and I hate going to sleep when I don't know what's wrong. So, but right before I was going to go to sleep, I figured out that this button is inverted, so it has to be held in all the time instead of being out all the time. So yeah, I'll fix that when I wake up. So I had a nice long sleep and I feel much better now, so I will continue after I had some breakfast. Yeah. So yeah, I forgot to tell you that this switch is switching on and off the load. So yeah. Yes, so it's working. It's a bit slow. I don't know, maybe it's something to do with my program when I ported it from the other ship. So something happened there. I had to fix this one, so I didn't show you that. So maybe I thought maybe it would be interesting for you to see what I fixed. But if I just show you, then you can see now it stopped there, like it should, and it moves in 5 millivolt steps. Anyway, maybe it's more interesting to show you the fault finding instead, so I will revert the change to get back to the fault that I had, so you can follow the fault analysis. I will show you this on the schematic instead. So you can see the power input there on the left. It goes in onto voltage regulators. This is a fixed 5 volt regulator which supplies 5 volt to the microcontroller, and then you have a adjustable voltage source. You have two of them. So the voltage, if we measure this, we should see 12 volt, 5 volt, 5 volt, and we should see 10.5 about, because there's always a dropout voltage over it. And then here you should see 5 volt. If this is running its program, the output here should start at 5.05. So, but the LED on this one was a bit dim, and when I measured the voltage out on the saver here, it was about 1 volt or something. So, and then I measured this one, it was around 0, and yeah, there about 0 or 1 volt. So this microcontroller didn't provide that voltage that should be here. So what was wrong then? Well, so I started measuring. So I started out here. Okay, so I didn't get the voltage I wanted. So I checked that the microcontroller had the voltage it needed, and it didn't. So so there was the fault right there though. So what happened? And you can see, I wasn't sure if I wanted to show you this, because yeah, these pads, they break so easily, so I have dunked it down down with the tin, so it keeps itself together. Anyway, in the beginning I said this switch didn't work. It worked the opposite way, it was inverted. And when I tried to invert it back, I did some mistakes. And I fixed those mistakes, but I made some new mistakes. And that was when I soldered this jumper, which goes to the 5 volt. This is the 5 volt output of this 5 volt regulator. The thing is, when you heat up these pins, you can see if I can. Let's take this one for example. This is a solder blob that joins these two together. See now? It's gone. I think that's what happened, because sometimes I lose my solder blobs, and this whole board is built up by solder blobs. So when I inserted that wire there, this jumper wire, well, yeah, I lost the solder blob right there. So the microcontroller didn't have 5 volt anymore. That concludes this video, so I will edit it and upload it, and yeah, you can switch it on, see it works. Click this one, start scrolling, and you can start meter. And you notice also I have the prototype saver, and that's because I have sent everything out, so I don't have any more. Yeah, about that. Okay, so I got a mail from this dirtypcbs.com. They had now produced my board. I thought they had already done that, but no. So now they are going to ship it, and I think maybe they have already done that. You can see it's very thin. Has been shipped, yeah, it's been. Okay, so the board will come soon. So I'm happy about this PCB in Fritzing, because it's not so easy to get by free programs that work so well. So they have a lot of parts that has already been made, and that's also a big problem when you get new software. There's always parts missing. But since I like this so much, I'm going to learn how to edit components such that I can get more flexibility here, because One problem I had is that these big ass resistors, they aren't this length, they are actually this length, but I can only select this, this and this and this. So you can't move like one pin length, you must move two at a time. So yeah, that was a little bit boring. So they did have their different types of regulators, because the pinout was different from the adjustable and the 5V regulator, so that was great. So, and here you can also see 19 of 20 nets routed. So why isn't all routed? Yeah, here it's missing. Like this. So yeah, routing complete using one jumper parts. So that was the aim of this, to put the components in such a way that the nodes, this net here is one node, by the way, like over here. You can see the ground node is here, I think. Yeah, this is the ground node. You can see it goes down here also. It's usually the largest net. So yeah, so I wanted as little use of jumper as I could, so I got by with only one. And this is the one that feeds back the output voltage back to the controller, and there's a voltage divider here. These two are voltage dividing and feeding it in here, because if you don't voltage divide, remember we have voltage here over the supply voltage of the microcontroller, so we need to divide it in two, such that we don't get over 5V in on the microcontroller. So thank you for watching, so we'll make some savers soon.